the first part of the thesis, that is effects of spectral normalization and multi-agent reinforcement learning. And then we look into the second part, where we'll focus on the framework MARL-JAX, which is a multi-agent framework which we have developed for social generalization and multi-agent learning. And then finally, we'll conclude the thesis and look at the resulting publication. So let us start with the background work. So what is reinforcement learning? Reinforcement learning is basically like where we want to train an agent to interactively learn from the environment. So the objective here is to maximize the discounted cumulative reward. So where, like, if you look at the formula here, capital T is the total time step of the episode for which the episode will last. That episode is basically the interaction of the agent with the environment, and then RK is the reward at some specific time. So basically, at each time step, the agent will perform some action, and then for that action, the agent will be rewarded. So RK is the reward which will be received by the agent at a specific time K. And then gamma is the discount factor, which controls basically how much importance we want to give to the reward that we receive, and how much do we want to consider it to be relevant in the future. So basically, it helps in maintaining the long-term dependency between actions and the reward. And yeah, so this formula basically summarizes the RL objective, and the objective of the agent is to maximize the cumulative discounted reward, that is GT. And now we'll define two key terms, that is the value function and the action value function. So value function or a state value function basically defines the what is the expected reward that we can achieve given that an agent is starting in state S. So let us say that during its course of interaction, the agent has reached some state S. So what will be the expected reward that it will be able to receive given that it is starting from that state? That is the value function. And similarly, action value function is defined as the expected return that it can achieve given that it starts in state S and it takes an action A. So here it is dependent on both the starting state as well as the action that it performs in that state. So these are the two major definitions which we'll be using throughout. Okay, in this case, if we already know the transition dynamics and the entire environment and the possible next state, so say that for the value function V of S. So given that we are starting in state S, and you can see that the expectation is conditioned on policy phi. So let us say that we are having a uniform random policy, we are starting in some state S, and there are 4 possible actions which are equally possible. So now in that case, and we also know, like, from that state, we have 0.25 probability for each action, and we also know the next landing state. So let us say it lands in S1 dash, S2 dash, or S3 dash, or S4 dash. So then we'll know the next state as well. So then we can define it as a recursive definition where we can write it as the expectation will be written as the say basically the probability of selecting a specific action, and then based on the action, the transition. So if transition probabilities are not known, we can just depend on sampling-based systems where we interact with the environment, assuming that we have environment available for interaction for infinite amount of time. So if we collect large amounts of data, then we will be able to compute this expectation. So our problem is formulated as a Markov decision process where it is defined using this tuple, which consists of the state space A. So these variables are basically used to define the RL problem. So state space S, that is what are the possible states which the agent can visit in its decision process. U represents the set of actions or control inputs, basically what all possible actions the agent can take throughout its interaction with the environment. P is the state transition probability matrix, that is basically landing in some state S given that it starts in state S and takes an action U. So this represents the transition probability. And then R represents the reward function, which is usually conditioned on the state space and the action, state and the action. So yeah, that is the reward. And then there's a discount factor which determines the trade-off between how much importance it wants to give to short-term rewards versus long-term rewards. In most of the real-world scenarios, like we are not able to observe the entire state, and that is the strong assumption that we have in Markov decision process, that the agent is able to observe the entire state which it is in. So, but that is not the scenario, and that is when the partial observability comes in, where it is only able to observe a really small partial part of the actual state it is in. So that is the only difference with MDB, where we have an observation probability matrix, which shows that we are able to observe some observation O, given that it is currently in state S and it is taking an action U and transitioning according to the transition matrix. So this is a major, say, deviation from the MDB. Now we'll start with policy gradients and actor critic method. So I'm directly jumping to policy gradients because most of our research is focused on deep RL. And that is why I just basically defined the value functions and all, which we'll be using it throughout. So a policy gradient is defined for, say, we directly want to learn a policy pi, which helps us select the optimal action given the agent starts in some state S. And this policy is parameterized by parameters theta, and we can use a simple neural network for that. And now given that neural network are trained using gradient descent and the rewards are not differentiable directly, so that is why this formulation comes in. So here the objective j pi of theta, that is the objective to maximize, given that we have a policy pi parameterized by theta. That is, we want to maximize the expectation, that is the expected return of the trajectory tau that we will be seeing, which can be sampled when we are following a policy pi of theta. And then we want to take a gradient with respect to it to optimize for the parameters theta. So that is the formulation. And like there's an elaborated derivation, but I'm just skipping it because it's standard literature. And the final formulation comes out to be basically the gradient of this objective is the expectation over the sum of gradients of the raw probabilities of the actions that are taken multiplied by the reward that is received. So this is the formulation of the policy gradient that is standard. And then there's a lot of variants of this policy gradient, such as actor critic, where instead of directly multiplying it with the reward or the return, we use the advantage function. So advantage function has a benefit over directly using reward is that it has a lot of less variance. So it helps in controlling the variance and hence in better convergence of the network. So advantage function is basically defined as the it is defined over state and action, given that it starts in state S and takes action U, and that is the return that is expected from that state and action, and subtracted by the return that is expected from that state. So this basically shows that what is the advantage of taking a specific action UT over all the other actions possible from that state. So that is how the advantage function is defined. And in practical scenarios, the advantage is used as QT, that is the action value function that we saw earlier, subtracted by the value function of that state. So this shows the advantage of the action that we have taken. So that is the advantage function. Now we look into multi-agent reinforcement learning, where there will be multiple agents interacting with the environment. Now, multi-agent reinforcement learning can have a lot of variation, and we can define it in based on the type of agents, the type of environment, we can classify it as given. So based on the type of agents, the multi-agent environment can be either homogeneous agent environment or heterogeneous agent environment. So in homogeneous agent environment, all the agents in the environment have the same state space, same observation space, and the same action space. So all of the agents in the environment will be able to perform only exactly same actions. Whereas in heterogeneous environments, the agents can perform different actions, and their action space might also be totally different. So these are the two variations. And based on the environment type, the multi-agent environment can be either cooperative environment, where all the agents in the environment have to cooperate with each other to maximize their cumulative sum of rewards, or it can be competitive environment, where each and every agent is working to maximize their own objective and not at all concerned about the other's objective. And then there are mixed environments, where there are some components of cooperation required and there's some form of competition as well. So they have some individual reward to maximize, as well as and that can be achieved only through some form of cooperation that they perform. So those are mixed kind of environment. So in the first part of the thesis, we'll look into mostly cooperative environments, and that will be for homogeneous agents. So I think in the entire thesis, we focus only on homogeneous agent environment. And in the first part of the thesis, we'll be looking only into cooperative environments, whereas in the second part of the thesis, it can belong to any of the three categories of the environments. So let us start by looking into cooperative multi-agent environments. So cooperative multi-agent environments are more the problems in cooperative MARL are usually found using DEC MDPs, that is decentralized partially observable MDPs. And the state-of-the-art approaches used to solve the cooperative MARL environments is known as centralized training, decentralized execution. And so we can train multiple, there can be multiple ways in which we can train all these agents. But one of the most simplest way which comes on top of our mind is that we train each and every agent to individually, and we have an assumption that that is the only agent interacting with the environment, and we totally discard the presence of other agents in the environment. And that is the most simplest approach. But the most optimal approach in the cooperative environment has come out to be centralized training, where each and every agent is aware of the other agent, and they have a common goal to achieve. And and basically, even though their action is during the say evaluation time, they can have decentralized execution, each and everyone working on their own, but their training is totally centralized. Okay, So in on-policy algorithms, the two commonly known are IPPO, that is independent PPO, which is basically based on the paradigm that I told you earlier, where each agent assumes that it's the only one interacting with the environment. And then there's MAPPO, which is multi-agent PPO, which is again following the paradigm of CPDE, where they have a common critic network. So that is cooperative multi-agent RL. Now, I said that cooperative MARL problems are formulated as decentralized FORM-DPs. So what is decentralized FORM-DPs? So we had looked at FORM-DPs, which was for single agent environment. But now in decentralized FORM-DPs, we have a few more definitions. So here the state space S is the state of the environment. And in this environment, there are multiple agents. Each agent can take action UI, where I is the agent ID. Which belongs to the action space U. I said that we'll be focusing on homogeneous agent environment. So they have a common entire action space. So each agent can, even though they have a common action space, each of the agent can have its own individual action, which might be different from others. And then finally, the joint action space, which consists of which is basically a tuple of actions taken by each and every agent. And then there is the local observation ZI. ZI is basically the local observation of the agent I, and this is partially observable. So we know that the entire state is S, but based on the location where the agent is in during that specific time step, it is only able to observe something locally around it. So that is the Z. And then there's this observation function, which basically leads to Z, given that the agent is in state S and its agent ID is I. And then tau I is basically the action observation history of a specific agent I. And then we can define the policy pi I, that is policy of a specific agent I, that is based on what action it. So this policy basically defines what actions the agent selects, that is UI, based on its own action observation history, that is tau I. And this is the decentralized policy of the agent I. And there is a common objective. We said that there's a centralized training. So for the centralized training, there's a common objective, that is maximizing the reward, given that it starts in state S, and it takes the entire joint action taken by all the agents combined in the environment is this U. So, yeah, now we'll define PPO and MAPPO. So 2 slides ago, we looked at the actor-critic algorithm. So PPO is a variant of actor-critic algorithm where we use the advantage function. Here we'll use a clipped objective where this advantage function, basically this gradient is clipped with some threshold. And this is done so that like it enables us to have multiple update steps per observation. And this helps in overall divergence and reusing the same observation again and again. And it has better convergence properties compared to the standard actor-critic method. And yeah, it also has a KL penalty, which basically tries to maintain the like distribution of the policy as close as possible to when it started using the same observation. So yeah, that is this term. And here this. So basically, when we have one update step, initially we start with policy. Say initially our weights are already theta old, but as we compute one step of update, our weights are updated, and then based on that, our policy changes. So that is why we have to do this important sampling reweighting, and that is what this row term is that is used here. That is reweighting the advantages based on the updated policy, and then there is a KL penalty between the updated policy and the old policy. Now, MAPPO is a multi-agent extension of PPO where there is a centralized critic, as I mentioned, and it has access to privileged information. So basically, the centralized critic can access the observations of all the agents together. So that is why it's called a centralized training, because it has centralized information of all the agents. And the centralized critic learns the joint action value function because we have a joint objective, and based on this, we'll be training the individual agent policy. So that is the MAPPO. So the policy network can be like each agent can have a separate network, but we used weight sharing in our implementation. But like I don't think it will create any difference because each agent is only able to observe its own observation during the actor part. Whereas in the critic part, it has access. So there's only one single critic because like it has a joint objective, right? Like mentioned here. So there's one joint objective. So there's only one single critic, and that is one common network which has access to observations of all the agents in the environment. Yes. That is a really like that is the best case scenario. But if we are working with multi-agent environment, we ideally like if we consider some practical examples, we want the agents to, even though we want them to cooperate, they might not be able to communicate with each other, and there might not be one central controlling agency always available. So like each agent should have its own policy independently. So that is why during the training time we have this privileged access of critic, but during the evaluation time, each agent can act independently. So I think there is a catch here, and there are a lot of like the system is overall quite fragile because it depends. Like it has a strong assumption that every other agent is performing based on its own assumption. So say there are two agents, and both of them have to cooperate for something, and we have trained them centrally. So now once we have trained them centrally, each of this agent has made some assumptions about how the other agent might be behaving, and it selects its own action based on that assumption. So if that assumption breaks, immediately the system will break. So this is the problem that we'll be focusing on the second part of the thesis.
Okay.
I'll talk about this in detail. Yeah. The common challenges are like in single agent. If the environment is really big, the exploration of the environment is a problem because we are achieving good rewards, but there might be possibility of achieving even more reward if we explore more. And then there's sparse reward. So probably we might not receive reward for every action we take. We might receive only at the end of every episode or something like that. And then there's partial observability, like because we are not able to observe the entire environment. We only have partial information to decide on our action. And then there's reproducibility. Like our algorithms are really dependent on hyperparameters and the implementation details that we make. And reproducibility has been a common challenge in reinforcement learning in general. And some challenges specific to multi-agent learning are exponential growth of joint action space. So you said that why not use a common central acting agency as well, just like we are doing the central critic agency. So in that case, the entire joint action space will grow exponentially. So let us say there are two agents and each agent can select 4 actions. So the combination will become 4 square, that is 16. So this is how the action space grows. And then there's non-stationarity introduced due to the learning co-players. So one of the assumptions that reinforcement learning makes is that the environment is static. But when there are multiple learning agencies in the environment, what happens is say I am a learning agency and there's one more learning agency. So when I'm learning something, I assume that when I take an action, the environment should behave in a very specific way, even if it's probabilistic. But its distribution is fixed. Its distribution doesn't change. But when there's another learning agency which is also affecting the environment at the same point of time, so basically the reaction of the environment and the distribution of the transitions will change over time. So that is what causes non-stationarity, and that is why having a centralized critic is really helpful. That is another challenge. And then there is slow experience collection because the environments are really slow and it is computationally expensive to run multiple agents and the environment overall. So let us say we are playing a game of chess. So in a game of chess, after every move, we don't know whether it was a good move or not. We only get to know after the game is over, based on if we win or if we lose, that whether the entire game was good or bad. So that is what sparse rewards. Sparse rewards is you receive rewards very sparsely throughout the interaction. Like given that we have taken a series of actions and now we are receiving one single reward at the end. So it is more about associating actions with reward. So like if we are receiving reward immediately, whether this move was good or bad, we know that that move was bad and we can change it immediately. But throughout the game, we might have made few really good moves and few bad moves. So and if we receive only one reward at the very end, we won't be able to say assign that this were bad moves or this were good moves, right? And we'll need a huge amount of data to be collected, and then based on the expectation that we calculate over the huge amount of data, finally it is more about credit assignment problem. And now this is the final part of the background, which is spectral normalization. So spectral normalization is basically normalizing the weight matrix by its largest spectral value. And this, in a neural network scenario, it constrains the network layer to be one listed continuous. And spectral normalization was introduced to stabilize discriminators in GAN. And we'll be using similar concepts here. And in context of RL, spectral normalization has earlier been used in standard value-based methods like DQN or actor-critic methods like DDBG. And they have applied the spectral normalization on the value function or the critic of these off-policy algorithms. So it is important to notice that till now, spectral normalization in RL literature has only been applied to off-policy algorithms and in single-agent techniques. Now we can start with the first part of the thesis, where we focus on learning in sparse rewards on policy cooperative MRL environment. So our focus is homogeneous cooperative MRL environment. We'll be using only on policy multi-agent algorithm, and the rewards will be sparse rewards from this environment. So, and our main contributions in this part are we introduce a sparse reward configuration for SMAC. SMAC is a StarCraft multi-agent challenge environment, which is a common benchmark for cooperative multi-agent environment, and show that it is difficult to learn when compared to standard reward configuration. So standard reward configuration is having quite dense rewards, whereas we introduce a sparse reward configuration, and we propose that then we compare the regular algorithms which fail really badly in this configuration. And then we propose to regularize the critic with spectral normalization and show how it helps in learning better policies under sparse rewards. And then finally, we analyze the effects of spectral normalization and show that it helps in stabilizing the critic gradients. And it also has optimizing effects of scaling the gradient, which scaling the gradients of the entire critic. And that's more of a theoretical part, which is described in detail in the thesis. So these are the two environments where we verify, where we benchmark our algorithms. So one is the robotic warehouse, where there are multiple racks and multiple agents, which so basically here is the entry point where, and the agents are based on the request coming. The agent needs to go and collect the specific box from the specific rack and deliver it here. And there's a StarCraft multi-agent challenge, which is a game environment where there are two teams. The teams can be imbalanced as well, but we'll be controlling only one of those teams, and all the agents will have similar action space and state space. And then we need to win against the opponent team, basically. So that is the other cooperative environment. Yeah, so now let us talk about the sparse reward configurations that we introduced. So in standard SMAC setting, the ally team, that is the team that the RL algorithm will be controlling, receives rewards for the changes in their own, basically it is basically considered to be a shooting game. So if the agents in their own team lose health, then they get a negative reward, and agents in their opponent team, if they lose health, they get a positive reward. So that is a very dense setting where if two agents are coming face to face and they are shooting against each other, there is always a health reduction going on either side, and that's why it is immediately receiving a reward. So in our case, what we do is the rewards are distributed only for the death and not for the reduction in health value. So this leads to very sparse rewards where an agent might need to go and kill an agent in the opponent team to receive some reward. So yeah, and it is not really simplistic environment where you just go and shoot once and the other person dies. No, you need extended planning between multiple agents to target one specific opponent and like that. So it involves quite a lot of strategic planning. And here, a standard MAPPO based network algorithm is used for verifying for benchmarking the environments, and we use a standard actor critic. So PPO based actor critic architecture, where the actor network is 3-layered recurrent network, where the middle layer is LSTM, and then there's a critic network, which is a feed forward network with 3 layers. So yeah, that summarizes the basic environment setup of the experiments. So now we'll look into what experiments that we perform. So we perform 4 major experiments to understand how spectral normalization affects. So one we do is full SN MAPPO, where we apply spectral normalization to all the layers of the critic. Then there is mid SN MAPPO, where we apply spectral normalization only on the middle layer of the critic. Then there is last SN MAPPO, where we apply spectral normalization only on the final layer of the critic. That is the output layer. And then there is standard MAPPO, which is used as a baseline. So now let us look at the results on robotic warehouse environment. So here we compare only mid SN MAPPO. We'll look into other algorithms for this MAC environment. So here we can see this environment is relatively simpler. Even though the rewards are sparse, they're not as sparse as the StarCraft environment. So we don't see a lot of benefits over here. But still, we can see that there's a little bit of faster convergence with the mid SN MAPPO in case of this environment. In all of these environments, in some case the convergence, the difference is much higher compared to the other case. So yeah, that's it. So that is the experiment on robotic warehouse. Now let us look into the StarCraft environment. Here is where the things get interesting. So if we look at MAPPO, which is the red line, we can see it almost never converges in the first environment. In this environment, it does converge, but its battle win rate is less than 0.4. It basically wins less than 40% of the battles, of all the battles that it is evaluated. And then there's the corridor environment, where it is able to win around 25% of the battles. So all of these 3 are super hard maps of the StarCraft environment. And so yeah, these require a lot of strategic planning. So, and these are selected because in this case there is a team imbalance where the team that RL is controlling has only 8 agents, whereas the opponent has 9 agents. The other environment, it has a lot of agents. So the ally team has 27 agents, which is a lot of agents. And how the algorithm centralizes here, and the opponent team has 30 agents only. And then this corridor, which is this environment's map is really peculiar, where the two teams don't come directly face to face on an open ground. There are really narrow corridors where the agents need to pass through, and they might get stuck in between. So this requires a lot of strategic planning. So like each of these three environment has its own unique properties. And yeah, so now we can see that the red one didn't, like, basically barely won around 5 to 10% of the battles. Now, when we look at mid SN MEPPO, where we are applying only in the middle layer, we can see that the performance increases quite a bit. And even if we apply it on the full, say, on the entire critic network, then the like performance improves even more. But we can see like there's a lot of variance. Like if we look at the standard deviation plot for the blue line, but when we apply it only on the last layer, we can see that even though it takes a bit longer to converge, it finally wins about 80% of the battles that it has totally played. And like the variance is also less. Like we run it for 3 different seeds, all of these algorithms, and then that is what based on this error margin is plotted on. So we can see like its convergence is much better compared to the other algorithms. Similarly, we can see this like results are on similar lines for this 27 and 30M environment where there are a lot of agents. So this algorithm even generalizes when there are like really huge amount of agents in the environment. So here again, the least performing is the baseline one. Mid SN is performing good, and mid SN and full SN MEPP are like the final scores are quite similar. But again, the last SN MEPPO is performing the best, where again it reaches an 80% win rate. But corridor is a really interesting environment. So as I told, like the map is really peculiar, and it can get stuck in between. So here we can see that last SN doesn't like get anything better than 0. It basically loses all the matches it has played. Whereas mid SN is able to reach a good place, but still the variance is really high. Similar is the case for like the standard baseline. And full SN MEPPO does start learning something, but like it is not consistent. So again, you can see it through the variance plot. So now we will look into like more details about why this is happening, like why it is not able to learn anything here, whereas it's learned really good, like the last SN MEPPO converge really nicely in these other two scenarios. So for that, we look at the gradient norm plots of the spectral layer. So of the layer on which we apply the spectral normalization. So this is the gradient norms of the entire network. My bad. So when we look at this in the corridor environment, we can see like MEPPO has really large variance. You can see that this is a plot on a log scale. So the baseline has really large amount of gradient norm, and its variance is also high. Whereas when we apply it in mid SN MEPPO, we can see like the overall gradient norm is reduced and it is in much controlled space. So we can see that this mid SN MEPPO converges much faster, at least compared to the standard baseline. So we can attribute to the fact that it is able to control the gradient norms, and that is why it is leading to better and maybe even faster convergence. Whereas the other two cases totally fail. So that's why we see like the gradient normalities are really low here. Next, we look into the 27 and 30M environment. So here we can see like the gradient norms somewhat lie in ballpark same range approx. So yeah, we couldn't say much about this. So like gradient norm is definitely helping. Like it is helping in controlling the gradient norm, but that is not the only thing that might be helping. So yeah, that is where the second part comes in. Okay, one more thing that we saw in corridor environment is that MEPPO and mid SN MEPPO are performing almost close. Like the win rates are really close. But when we look at the number of dead enemies in the opponent team, we can see like mid SN MEPPO is consistently doing better than MEPPO, and even full SN MEPPO is doing almost as good. Like it is this basically shows that full SN MEPPO is not able to kill all the enemies in the opponent team, but it is able to kill as good as number of enemies as the MEPPO is doing it. So like win rate is not, it's just one parameter that we focus on. But when we dig a bit more in detail, we can see that even though the win rate is similar for mid SN and the baseline, the kill rate is always better. So that is another interesting observation, which shows that like applying spectral normalization is definitely helping. It's just that this map is specifically very complicated. So yeah, now let us look at the benefits and drawbacks of applying spectral normalization to the critic. So one of the benefits is just like we looked at in the light slide, it helps in stabilizing the critic by constraining the gradient. Another is the optimization effect. That as we discussed, that it will scale the gradients by the inverse of the maximum spectral value. Or if you are applying it on multiple layers, the product of the maximum spectral values of each of these layers. It helps in better learning of smooth value functions. So we saw that the last SN MEPP was performing really good. So when we are applying spectral normalization only on the last layer, it is constraining the last layer to be one Lipschitz smooth. That basically means the output, that function is one Lipschitz smooth, and the output of that function will always be one Lipschitz smooth. So now when we are applying only sparse rewards, learning of the function might be very complicated. And if it's a really high frequency function where there's no constraint on the smoothness, like learning each and every value, like it might need a lot more data. But in this scenario, because we are applying spectral normalization, what happens is even if the say the data is really low, it is able to converge because of the smoothness constraint that is applied. But it is only limited to the conditions where the value functions are smooth for that environment. If the value functions are not smooth, like in case of corridor itself, like as I mentioned, that corridor has really narrow pathways where they need to strategize properly. So the value function might not be smooth when we like look at the smoothness in the input space. Like it is not smooth compared to the input space. So because of that, what will happen is just a small deviation in the input might lead to a large deviation in the output space. So that's why it is not really smooth, and that's why like that is our hypothesis that is the reason why it is failing in the corridor scenario, the last SN and MPPO, whereas it is performing really good in both the other environments where like they come in an open ground, so the value function will be really smooth overall. Yes, so we are applying TPO, right? So we want to reuse the input data as much as possible. So what we do is we collect it for around, say, I'm running it as a parallel process. So I run 10 parallel processes, I collect 10 episodes, and then I train on this 10 episodes for around 4 epochs. So, and this training happens is one update for the policy network, one update for the critic network. So that entire process on the same data for 4 times. And then again, I collect another episode. Take longer time training, whereas introducing spectral normalization is helping us converge faster. So definitely, like getting more data is always helpful in case of neural networks. The thing is, we can't have quicker updates earlier because there are sparse rewards, and we only receive 0 rewards earlier, unless and until we actually start doing something. So initially, it is doing total random exploration until it converges, until it stumbles upon one specific rewarding state randomly. And once it has stumbled upon that, there's a lot of data imbalance. We need to handle that as well. And now with applying spectral normalization, even if there's data imbalance, whenever it is trying to match that, because of the smoothness constraint by applying spectral normalization, what happens is it slowly starts like converging to that value for that specific. Even if it starts slowly because of the imbalance, it does learn something. Whereas if we are not constraining it at all, what will happen is it'll have 0 values for all of these states, and then suddenly there will be a jump, and then again it will be 0. So applying the smoothness ensures that it is learning like this. It is basically smoothing out that if this state is a rewarding state, maybe states around it might also be rewarded. So that is why I believe it is leading to faster convergence. We are already doing mini batch gradient descent, and like batch gradient descent is like because with every update our policy is updating, our data distribution also changes because as soon as the policy updates, we get better experience. So all the experience that we have collected till now is almost useless. Okay, and the drawbacks are like spectral normalization can only help up to some extent. As I mentioned, that it only helps in learning smooth value functions under the conditions that agent is able to reach rewarding state as well. So if the rewards are so sparse that it is not at all like with random exploration, it is not at all able to reach the rewarding state. So we also tried one more setting actually, where we only reward for the win or losing, or like battle win or battle loss, instead of for the death one. In that scenario, none of the algorithms converge. So like it does help in sparse reward scenario, but it is only helpful under the conditions that it is able to reach at least rewarding state, even though very rarely. And then when we are applied to the final layer, as we saw that like it only helps when the value function is smooth with to the input state. So yeah, these are the two drawbacks I believe. So when it be plus 1 reward, I also tried scaling the reward, scaling it to plus 100 or plus 500 like that. Totally agree to that, but again, like the first problem comes in where like it is under the condition that the agent is able to reach some rewarding state under random exploration. It doesn't reach the battle winning state under random exploration at all, because like this is a really extended game, right? There are multiple agents in the opponent team as well as your team, and opponent team already has knowledge and skill to beat you, whereas you have to strategize and beat the opponent team. And like stumbling upon that entire episode of winning in such a complicated scenario with random exploration. How can we extend this work? So while our work mostly focuses like successfully addresses moderately sparse rewards, just like we discussed, uh, like we really want to see like how could we solve highly sparse rewards. So maybe like just constraining the network weights might not be enough. We might have to introduce some smart exploration strategies as well. The other scenario is in this work we primarily focus on cooperative environments only. So it'll be interesting to see the effects in competitive games or general sum games or mixed sum games, and how it translates to other kind of multi-agent environments. And yeah, other thing is like we only tried spectral normalization. That is one of the regularization techniques. But maybe we can again try something like batch normalization, layer normalization, or something like that, which could further help improve the performance overall. So next part we'll look into MARL-JAX, which is a multi-agent framework for social generalization. So here our goal was to develop an open source scalable framework for multi-agent learning, which caters to social generalization research. So this didn't start like this. It basically started like we wanted to focus on social generalization in multi-agent, but there were no libraries or any code base available, and that is why we started developing it on our own. So, our major contributions are we develop a JAX-based framework for training and evaluating social generalization for training multi-agent policies. And it is loaded with features like we include as many features like multi-GPU training, distributed experience collection, and everything. So, yeah, this is a really highly scalable framework depending on the number of resources that the user has. And we evaluate our implementations on two strong baselines. That is one multi-agent actor critic. This is an independent actor critic, unlike the ones that we used in the previous part, and options as responses. So this is a algorithm from DeepMind, which is specifically designed for social generalization and multi-agent checking. And we evaluate it on two commonly used benchmarks. One is Melting Pot, which is developed by DeepMind, which is focusing on social generalization, and one is Overcooked, which is it is ideally a cooperative environment, but like in this, the agents have to cooperate with each other, and we can develop interesting social generalization scenarios where when the policies are trained independently. So yeah, we focus on this aspect. So these are the supported environments. The left side we can see one of the environments from the Melting Pot suite, and on the right side we can see one of the maps from the Overcooked suite. So yeah, so Melting Pot, like specifically designed, as it is specifically designed for social generalization, it defines some key terms, and I'll be going through those first. So substrate is basically an environment. It is a multi-agent entire environment. That is substrate. Background population is basically, let us say, it is an entire game, and we have some pre-trained policies available. So let us say for some k which is less than n, we use some pre-trained policies, and we use those policies, pre-trained policies, as uh, the action selection property for those population of k agents, and combining the substrate with the background population leads to a scenario. So as we keep on changing the background population, it leads to different scenarios. So substrate is what we will have access to during our training time, whereas for evaluating social generalization, what we'll do is we'll design some background population with peculiar properties. Like let us say we are having a cooking game in Overcooked. So it is a two-player game where one has to cut, both of them have to totally cut the vegetables, boil the vegetables, and then cook the soup, and then serve it. So there are like 3-4 steps. Now, if we are training it in a cooperative way, let us say one agent learns to cut and boil the soup, other agent learns to add some ingredients and probably serve the soup. So if we have trained these together, if the other agent is trapped out and we put in some other policy which knows only how to serve it, then the other agent should be adapting to the new agent that has come in, that it needs to cut and boil the soup because the other one in the present in the environment is only able to serve it. So that is a kind of generalization. We call it a social generalization. So yeah, we can have various kind of background population in the scenario that I mentioned, and then that will lead to specific scenarios where the background agent only needs how to cut it or how to boil it or how to serve it. So yeah, so scenario is basically a multi-agent environment with n minus k players, where k is the size of background population. So these are the terms defined by Melting Pot. And yeah, I think social generalization, this is just a visual representation where we see that, let us say in a substrate, we train all of these policies. Different color represents different policy. And during evaluation, there are multiple forms of evaluation. So let us say one form of evaluation is we randomly sample policies from this distribution, and they should be able to achieve as high reward as possible. So we can see that blue policies are sampled twice, yellow ones are sampled thrice, and like that. So basically, the distribution of the population changes overall. And even in that scenario, it should be able to generalize. That is the problem of social generalization. Or maybe we just sample one specific agent. And this basically answers the question, like, what if everyone is behaving like me? How will the reward of the entire, like everyone in the population be? And then there's the scenario where we can see that these colorless blocks are some background population policies, and the other ones are sampled from our trained policies, and then we evaluate it. So yeah, I think, and this is the evaluation criteria, which is basically the mean of the rewards obtained by all the agents. So yeah, now I'll go into implementation details, as this is mostly software implementation work. To like have a, like the most basic implementation is like sequential training. We have a policy which interacts with the environment, it collects experience or batch or trajectory, and then the learner updates the parameter. And then these keeps on happening sequentially. Like once the learner has updated parameters of policy, it will again collect the experience. And yeah, this is a sequential process. So now we can optimize this process a bit more by having, say, instead of having a single environment interaction, we can have multiple environment interaction, and we can parallelize this across different processes. So all the environments can act in parallel. So this does speed up the entire training pipeline a little bit, but because of the synchronization step, there is still a little bit of bottleneck over here. So then we look into asynchronous training pipeline, where we have multiple processes, where each of the process has its own policy weights and its own environment, and the experience selection basically happens on CPU entirely. And then all of these experience selected is sent to a common replay buffer, and then there's a learner which keeps on continuously sampling from this replay buffer and updating the weights. And yeah, this processes on regular intervals keep on pulling the updated weights from this learner. So all of these processes are running in parallel. So there's one process of replay buffer continuously active, there's one learner which is continuously active, and there are multiple experience selection processes which are continuously active. The learner runs on GPU, whereas everything else runs on CPU. So this we found it to be a really fast implementation. A lot of standard RL papers like from DeepMind have implemented this kind of architecture, but I think we are the first ones to do it for multi-agent settings. And then there is asynchronous training with the common instance server. So as I mentioned here, like all of these entire experience collection process is happening on CPU. And as we are using neural networks, it might be really slow and bottleneck overall. So then there's this another proposed architecture in one of the DeepMind paper itself. So I don't think there's any open source implementation available for this. We are the only ones who did this and open sourced it totally. So we run multiple processes. Each of these processes will have multiple environments, and this process will receive an action, it will perform an action from the environment, it will receive the next state. Now the next state is again sent back to a common instance server which runs on GPU continuously. And in the meantime, while this environment is waiting for an action, we can always have 2 or 3 instances of environments in the same processor. So that way there's like maximal CPU utilization as well as GPU utilization, and this overall speeds up the entire pipeline quite a lot. So yeah, these are the 4 implementations that we do. And yeah, now we can look at the results. So this is melting pot environment called as running with scissors in the matrix. This is basically an environment where there are 2 agents, and there are like resources like rock, paper, and scissors. So these agents, what they need to do is they need to go and collect the resources that they, based on the game they would like to play. Say one agent wants to play a rock game and the other agent wants to play a paper game. So they collect their respective resources and then they come and play with each other. So basically paper always beats rock. So that's why this paper agent gets the reward and the positive reward, whereas the rock agent gets a negative reward. So in this scenario, social generalization can be achieved. Like this is a substrate training. So if both the agents are trained together, they'll know what the optimal policy of the other is, and then the ideal result will always sum to 0. But now let us say we are designing specific scenarios over here. We can see scenario 0, 1, 2, 3, 4. So these scenarios are unique, where in scenario 1, the background agent always plays rock. In scenario 2, the background agent always plays paper. In scenario 3, the background agent always plays scissors. And in scenario 4, it plays one pure strategy that is either of rock, paper, or scissors, but it is selected at random in each episode. So we can see like this options and responses paper that we have implemented that is able to achieve positive score in all of the scenarios. Whereas in standard actor critics algorithm, we can see that it loses badly in 2, it gains decently in the other 2 environment, and it performs almost neutral in the third environment, in the last one. So we can see like this algorithm is able to achieve social generalization. So which validates our implementation quality as well. And yeah, we can see like the training plots as well. Like we can see the standard access critical is almost always near zero, whereas the options response is like initially to zero, but then start gaining positive rewards overall. Even though the variance is really high, but yeah, it is able to receive positive rewards overall. So that is one environment. Then we do the same kind of evaluation in overcooked environment. So yeah, this kind of validates our implementation, and we run all of these algorithms for say 3 different seeds and then average it across 3 seeds. And same we do for the evaluation plot tables. So yeah, I guess that summarizes how this works. So based on this, the future work can be like our code base like can serve as a really strong foundation for future research on social generalization. Like this is a really new field where like only very few researchers from DeepMind or few other universities have been working on this. And yeah, our implementation focuses mostly on speeding up experience collection because the environments that we're using are always on CPU. So like given that Google has recently released JAX, which enables like GPU-based, say, mathematical computation, and it has been widely adapted across DeepMind and across the research community overall. Maybe like the community next steps would be to start writing environments in JAX itself, so that it will be able to run on GPU-accelerated devices and gain the benefits of GPUs, multiple compute, like say, yeah, high-performance computing. So that could be the future work. Yeah, I think that summarizes this work as well. And so in the first part of the thesis, we address the issue of learning a reliable critic in multi-agent fast-forward scenario. And in the second part, we introduce MLJAX, which is a software package for multi-agent RL, which focuses on training and evaluating social generalization of the agents. And these are the 2 resulting publications. With the first part of the research, we got into a paper into IJCN main conference. And with the second part, we got a demo paper at ECML